So beta DC is listed as capital HFE and beta is small HFE. Almost both the betas are comparable and you can use the same value for other for if any one value is given to you, then you can use that for preliminary analysis. Then we have some notation used for AC and DC values. For AC we are using the capital letters, and for DC we are using the capital letters, and for AC we are using the lowercase letters that you can see here. Next topic is AC resistance of the emitter diode. Whenever the input voltage source we are applying to emitter diode, input voltage is available across the emitter diode and it will produce the AC emitter current, and the value of this current depends on the Q point. So this is the graph of current versus voltage. Whenever you apply the AC input voltage, you will see the variation in output AC current based on the value of Q point. This variation will change. So let's see how if I the same value if I apply at a higher Q point, assuming that this is my Q point, then the variation in the current will be higher, that you can see here. Okay, so for the same amount of voltage, if your Q point is higher, the variation in current will increase. So it, in a turn it says that input impedance will decrease. IE is combination of IE is combination of AC plus DC. IE is a combination of AC plus DC. VB is combination of AC plus DC. The peak to peak value of IE depends on the location of Q point that we have just seen. The AC emitter resistance is defined as RE dash VB upon IE. So here, if you see the dash used in RE dash is a standard way to indicate that the resistance is inside the transistor. We have RE dash equation available. So for assume that base emitter voltage 5 millivolt and emitter current 10 microampere peak to peak, then RE dash will be 50 ohm. For the same value of voltage, if my emitter current increases, if I consider Q higher Q point, then definitely variation in I will increase that we have just seen. So the resistance will decrease. Okay. Formula for AC resistance. So the formula for RE dash is found by using a solid state physics and calculus. We have this formula readily available. We will use it, and it is applicable to all the transistors. However, for commercial transistor, the gradual non-rectangular junctions, there will be some variation in these values. It will be 25 millivolt to 50 millivolt. The reason RE dash is important because it is used to measure the voltage gain that we will see in the next lectures. Here, if a base bias amplifier is given to you and you want to find out the value of RE dash, so we need only one value, that is IE, so that you can find out using the DC analysis, find the value of IE, and you can easily get the value of RE dash. Now, to perform the AC analysis, we need to represent the transistor in its equivalent AC equivalent circuit. So for that we have two different models, T model and pi model available. T model is called as Ebers-Ball model. Here the emitter diode of transistor acts like an AC resistance RE dash and collector diode acts like current source IC. So see how T model is represented. This is the emitter diode represent as sorry emitter diode represent as RE dash, that is RE dash, and output collector diode is represent as current source. When an AC input signal drives the transistor amplifier, and in AC emitter base voltage VB is across the emitter diode, this produces an AC base current IB, so that we have seen. So if you look into the figure 9.17b, then we from input side we can see if we are applying this voltage and we are getting this current, then we can see some Z in base, that is the input impedance. Looking from this side, the AC voltage source is loaded by the input impedance of the base. Looking into the base of transistor, the AC voltage sees an input impedance Z in base. Z in base equation will be VB upon IB, and we know the equation of VB is nothing but RE upon IE into RE dash using the Ohm's law. So this value VB is IE into RE dash. If we replace here, then it will be IE RE dash upon IB, and IE you can replace by IC, so it's IC upon IB, it's nothing but beta RE dash. So our Z in base, that is the input impedance, will be beta RE dash. So this value will be beta RE dash. So the pi model is easier to use than T model because the input impedance is not obvious here, that is beta RE dash. We can see easily in pi model. In pi model, your base will be represented as input impedance beta RE dash, collector is grounded and emitter is grounded, and collector will be represented as the current source. Similarly here. So see the comparison between pi model and T model. Input current IB, this is IE/IC, that is your T model, and pi model represents the input impedance. Now, when you know both the analysis, sorry, both the models for analysis, pi and T, now we will look into the analyzing an amplifier. So we can have simultaneous effect of both DC source as well as the EC source available. So we will first perform the DC analysis. To perform the DC equivalent circuit, what we can do, we can open all the capacitors and we can get the EC equivalent circuit, DC equivalent circuit, and then you can solve for current and voltages. That will be used to find out the value of RE dash. For the AC effect on DC voltage source, you can see here, if you supply some AC voltage here, then there is no chance that you will get here some variation in the voltage available across this. Your voltage across this cannot be changed. The DC voltage source has a constant voltage across it, therefore any AC current flowing through it cannot produce an AC voltage across it. Here you will have no AC voltage present, so it is as good as connected to the ground. The same thing you can tell in a different way, that if you perform a superposition theorem, then one source will be made ground. So when we see the effect of AC, the DC will be grounded, and when we want to see the effect of DC, this will be grounded, and then you can add the summation of both to see the effect in superposition. Okay, now go to the next slide.